Good afternoon, dear participants. My name is Andrei Cherkassky. I am the Deputy Director of the Institute of International Relations. I'm pleased to welcome you to our webinar, Visual Analytics for Monitoring of the Distributed Computing Infrastructures for Large-Scale Scientific Experiment. I'm pleased to pass the floor to our current speaker, an employee of the Laboratory of Computational Experiment and Modeling of the Scientific Research Computing Center of Moscow State University, participant of the ATLAS experiment, Maria Grigorieva. Maria, please take the floor.
Okay, thank you. Is everything okay with the sound? You can hear me?
Yes, it's okay.
Okay, great, thanks. Andrei, thanks for the introduction. A short overview about myself and about my work. As Andrei have already said, I'm working at the Lomonosov Moscow State University at the moment, and our current work is about the monitoring and analysis of the functioning of the computing infrastructure of the LHC. We have a joint team from Lomonosov University, from MEFI, and we collaborate with CERN, and we carry out several very interesting projects, and in this lecture I plan to talk about these projects, not about all, of course, because I think I can't cover everything in one lecture, but I'll tell about two the most important directions of our research. So, a short outline. First, I'm going to describe CERN computing infrastructure. We will talk about the scale of this infrastructure, about some components, especially about networks. Then I'll present the system of the visualization of network roads, which was implemented by MEFI team, and this tool was highly appreciated at CERN, and it's been already integrated in CERN computing infrastructure. That's very good result, I think. So next topic is about the operational intelligence research project at CERN, which is totally devoted to the intelligent methods of data analysis, which is also very interesting. And in terms of this big project, the income of our team is the development of the cluster log framework. And I'll tell a few words about this. Of course, our work and our research is not limited to it, but I think that for one lecture it's more than enough, because the material is not easy to comprehend. So let's start from the beginning. I don't know, maybe you know about the LHC, about the CERN, and maybe you don't know, but I just want to be sure that you know what's this. And so that's why I made this overview slide about the LHC. So the LHC is the accelerator of particles, and it pushes protons or ions to near the speed of light. And it consists of 27-kilometer ring of superconducting magnets. You can see it on the picture, this 27-kilometer ring. And it has a number of accelerating structures that boost the energy of the particles along the way of this ring. What's the goal of the LHC, and what was the purpose why it was constructed? The goal is to fill some gaps in the standard model of particle physics. So the standard model is a theory which was developed in the 70s and describes the fundamental particles and their interactions. but the standard model is incomplete and it leaves many questions open. And the LHC was constructed to help to answer these questions. And what's these questions? I outlined some of them. For example, one of the questions is, what's the origin of mass? You know that the standard model doesn't explain the origin of mass, why some particles are heavy or some particles have no mass at all, for example, photons. And there were a theory about Higgs field. The particles that interact intensely with the Higgs field, they are heavy, and those who are that have feeble interactions are light. And in 2020, CERN announced the discovery of Higgs boson, which confirmed that this theory is but this theory is still under investigation, and there are a lot of questions still, but it was a very good result of working of the LHC. There are a lot of other questions which are not less important. For example, what's the supersymmetry, about dark matter and dark energy. Maybe you know that the matter which we know, and this matter makes up all stars and galaxies, and it accounts only 4% of the content of the universe, and all the rest is dark matter and dark energy. It accounts 23 and 73%. So LHC helps to investigate this phenomena. Also, there are some investigations about antimatter and about quark-gluon plasma. So I listed just a list of the biggest investigations which provided at CERN. And what should be noted here, the biggest experiments at CERN are ATLAS and CMS, and it's the general purpose detectors, and they investigate a large range of physics phenomena. Also, it has ALICE and LHCb experiments, but these detectors are more specialized, and they are focusing on specific phenomena. But we are not going to dive deeply into these complicated questions of particle physics. Let's move on. LHC, of course, has a great contribution in the development of, in the evolvement of high-energy physics. But besides, it has become one of the largest polygon of the research in big data. As the LHC and all its experiments generates vast volumes of data, it has very complicated and diverse computing infrastructure. And this infrastructure is constantly growing, changing. Now CERN is one of the most highly demanding computing environments in the research world. Computing is at the heart of CERN infrastructure. Computing contains hardware infrastructure, software, data processing, data analysis, data management, data storage, networks, and so on. And all this environment is used to support for the LHC and non-LHC experiments at CERN. I provided these numbers for you to understand better the scale of the LHC. For example, data center at CERN consists of 230,000 of processor cores and 50,000 servers, which run 24/7. CERN experiments generates large volumes of data, about 90 petabytes per year, and additionally non-LHC experiments add 25 petabytes of data each year. Data flow is also very fast. It's about 25 gigabyte per second. And the data storage consists of 70,000 of disks and 70 tapes. The storage, distribution, and analysis of all this data is provided by the worldwide LCG Computing Grid, WLCG. And the next slide is about the WLCG. So WLCG is a big project. It combines the computing resources of about 900,000 computer cores, from over 170 sites in 42 countries all over the world. So we can say that WLCG is a massive distributed computing infrastructure, and it provides more than 12,000 physicists around the world with the near real-time access to the LHC data. And it provides the power to process this data. It runs over 2 million tasks per day. Tasks, I mean physics analysis and data processing tasks. And now global transfer rates regularly exceeds even 60 gigabyte per second. The network infrastructure of the WLCG consists of a lot of devices. For example, it has 300 routers, 5,000 Wi-Fi points, 4,000 switches, and in general about 300,000 connected devices. And about the data storage of WLCG project, it has now exabyte data storage, 500 petabytes on disks and 500 petabytes on tapes. CERN provides about 20% of the resources of WLCG. One of the most impressive components of the WLCG is its networking and connectivity. It provides the distribution of data to the hundreds of collaborating institutes all over the world. And all this is possible thanks to the excellent connectivity and networking infrastructure at CERN. WLCG is made up of 4 layers, or they call it tiers, 0, 1, 2nd, and 3rd. Each tier provides a specific set of services. For example, tier 0 in the center of this picture is the CERN data center. It's located in Geneva, Switzerland. All the data from the LHC passes through this central hub. Tier 0 is responsible for the safekeeping of raw data from all detectors, from all experiments from the LHC, and the first data reconstruction. Next tier is tier 1. There's a 13 large computing center which have sufficient storage capacity, and they're responsible for the safekeeping of proportional share of raw and reconstructed data. And also it provides large-scale reprocessing and safekeeping of corresponding output, and distribution of data to the next tier, to tier 2. Tier 2 are typically university and other scientific institutes which can store sufficient data and provide some adequate computing power for specific physics analysis tasks. And currently there are about 160 tier 2 sites covering most of the globe. And tier 3, these are individual scientists which access computing facilities through local computing resources. It can be some clusters, local clusters at university department, or even just an individual personal computer. WLCG has such a multi-tiered structure. And at the beginning, this model had the hierarchical structure. It means that data from tier 0 transferred at tier 1 and from there to tier 2. Only in this direction. But later it became more flexible, and as networks showed robustness, good capacity, so now data can be transferred in any direction between tier 1 and tier 2. It's just important for the understanding of the complexity of the structure. In fact, the network proved to be one of the most reliable components of the WLCG architecture. And thanks to the constant progress in the network industry, the capacity has grown very well beyond the initial expectations. So LHC uses private optical networks which separate the LHC traffic from other global internet networks. CERN currently has two main private networks. These are LHC OPN and LHC1. LHC OPN, optical private network, was deployed to enable distribution of data from tier 0 to tier 1 sites, and also to support data movement between tier 1 sites. And LHC1 supports the data movement between tier 1 and tier 2 sites. So I see that the internet connection is unstable, so I'm sorry, I'll turn off my video. Maybe the connection will be better. I'll turn on video later. So okay. So I'll stop at the LHC1. So LHC OPN is for tier 0 and tier 1, and LHC1 is provides data movement between tier 1 and tier 2 sites and between all pairs of tier 2 sites. And you can see the complexity at these pictures, the complexity of the network connections between all data centers all over the world. So it's very complex network environment. It should be noted that network connections between tier 1 and tier 0 are built on a very well-provisioned private optical network, because these networks are responsible for the transfer of the raw data from the LHC. It's very important for these channels to be very reliable. So these connections are enough stable. But the mesh of network connections between tier 1 and tier 2 sites and between pairs of tier 2 might have frequent problems with connectivity and data transfer performance. And it can cause some problems. For example, the connectivity between two sites can be very low. And to fix this issue, sometimes it can spend several days. To ensure sites and experiments can better understand and fix networking issues, CERN started to use specific software, perfSONAR. It's a web-based, web service-based infrastructure, allows to collect and publish network performance monitoring metrics. So the next slide is about this tool. So a primary goal of perfSONAR is making it easier to solve end-to-end performance problems. It contains a set of services which measure different performance metrics in a federated environments. And currently, perfSONAR instances are installed at more than 120 CERN computing sites or CERN computing centers. And they provide ongoing collection of network measurements like network topology, latency, packet loss, and through output. Network measurements, of course, needs some visual representation for the analysis, for operators who monitor the network. And this slide shows the WLCG perfSONAR dashboard, which uses by the operators who monitor network connections. As you can see here, the characteristics of network connections between all pair of sites of tier 0 and tier 1 are shown here as matrices. Left picture shows the bandwidth. It means how many gigabits of data can be transferred over the network per second. And visually, this is represented as a matrix. Each element of this matrix shows a metric between a pair of sites, of computing sites. And color of the box is characterized as a quality of bandwidth. If green, good through output, red, bad through output. So, middle picture describes the network delay or latency. After how many times the packet sent from point A will be at point B. And again, the same matrix representation. Finally, on the right, you can see network roads matrix representation. It shows the number of network roads between each pair of sites for a specific time interval. For example, if the road between site A and site B hasn't changed for some time period, then this road, network road, is considered to be reliable, stable, and it's highlighted with green color. If there are more than 2 roads between these sites, it means that connection is less stable. The corresponding boxes are highlighted with yellow or red color. But besides the fact that we have the information about the number of roads, we can see what kind of roads are these, what is their length, how optimal they are, and we need sometimes to reconstruct the network path, network road, to analyze it. And this task was addressed to our team, and the team from LIFI developed a specialized tool for this task, which includes 3-dimensional graph visualization. And the next slide, I'll present this tool. But first, a few words about the network routing. What's this and how it's measured, and which information we use for a visualization platform. So network routing is the process of selecting a path in a network or between or across multiple networks. A packet delivery route between networks is constructed through transit nodes, which is called hops. It can be, for example, routers. Network routing provides the study of the network. It chooses the optimal route and transfer packets from the source to the receiver. And these network routes can be specified administratively, for example, by system administrator, and then it's static routes, or it can be calculated using specialized routing algorithms based on information about the topology, network status, or some other parameters. Then these routes are called dynamic routes. In our case, we deal mostly with dynamic routes. For a router, the route selection criteria may include the network bandwidth, the communication channels, if they overloaded, for example, delays, number of intermediate transit nodes, and reliability of channels. So it takes into account a lot of network characteristics to choose the most optimal network route. Network routes in CERN networks are measured by perfSONAR instances at each computing site, and all these measures are periodically saved in special storage. And for example, here on this picture, you can see one network route between two computing sites at CERN, between site A and site B. The route consists of 7 hops. It means that when data is transferred from site A to site B, it goes through 7 routers. And for each routers, we have IP address, as you can see it. So perfSONAR instance sends packets between sites and recorded these routes with all necessary data. It records IP address and host names. Additionally, perfSONAR measures time before each hop, before each router. And all this data is stored in a database. This data were used to develop the perfSONAR visualization system. This slide shows the interface of this system for visualizing network routes between LCG sites. So in the left pane, you can select some time interval. You can select also source sites and destination sites between which you want to see the network routes. And all network routes between the selected sites in the selected time interval will be visualized in the form of directional 3-dimensional graph. Each node is represented in the form of sphere. Lines are connections between them. The purple sphere is the source. The blue one is the destination. And the red one is the sphere with no source in the database. For example, some values, some parameters may be missed in the database, like IP address or time delay. And it means that perfSONAR couldn't measure these values, and it indicates that there are some problem with the perfSONAR measurement and problem in network route. So below the main picture, you can see the summary table of all routes, and you can select any row in this table, and the network route that corresponds to this path will be highlighted on the graph using animated small spheres passing between all intermediate nodes, hops. The speed of movement of small spheres shows the speed of data exchange between nodes. And on the graph, on the right, on the histogram, you can see the time delays to each internal hop. This is our visualization. The next slide shows that you can select another row in the table, which is below. And you can see that in this case, a different road is highlighted on the graph. So we can view all existing network paths in particular time interval. Next, what we can do here, we can also aggregate existing paths, existing network road, and see their average representation. This way we hide the similar roads. It's useful when we analyze, for example, network roads for a long period of time, because where we analyze, for example, a day or a week, there could be too many lines, too many roads. And each line corresponding to the perfSONAR road measurement. But we don't need all of these measures. We just need only roads. So we can just fold up this. Next slide shows an example of data analysis that can be carried out in this visualization system. For example, in the selected time interval, we examined the path, the network roads, between two pairs of sites. Red balls indicates that certain routers do not respond to a request from perfSONAR tool that tries to measure the network path. And a loss of network path data is observed at the nodes of the graph at the beginning, at the end. We can see the red spheres. These nodes didn't respond during repeated measurements, and the path itself reached the final node. So we can see that the path is completed. So we can assume that these these data losses occur due to the security settings of the respecting routers. This is just an example of the possible analysis. The next slide shows a case with the self-cycling routers. You can see that a router repeatedly transmits data to itself. It's self-looped. And as a result, all packets are lost, and data transfer from site A to site B is interrupted, and all the road is red. So the road is not completed in this case. And here we can clearly say which routers are self-looped. You can see it at the beginning of the road and at the end. And we can initiate a change in their configuration settings. So it's one of the most representative example of the possible data analysis using this tool. So as I've already said, currently it's already implemented, and it's within the CERN infrastructure. It's the income of team from NIFI. And this was the first part of my talk. It was devoted to the networks, and the second part will be devoted to the operational intelligence project. Operational intelligence project is completely another direction of the research. It's a joint effort of high energy physics collaboration, and its main goal is to reduce the operational costs of complex computing infrastructure by increasing the level of automation in operations. And this will be achieved through the development of stack of intelligent tools and technologies which aims to detect, analyze, and predict some anomalies in the computing environment, to suggest possible actions and automate operation procedures. Examples of such tools are smart alerting systems, recommendation systems for the operators, or predictive maintenance throughout log analysis. And the landscape of applicable technologies and methods includes, but not limited to, data mining, machine learning, predictive analytics, interactive data visualization, visual analysis, natural language processing, deep learning, neural networks, and so on. So here we have a lot of intelligent data analysis, intelligent analysis of big data. That is very interesting and very important. CERN itself has very complex, heterogeneous, and dynamically changing environment. And the monitoring, operation, maintenance of the computing infrastructure must guarantee, on the one hand, constant and utilization of the available resources, and on the other hand, high data throughput according to the physics goals and priorities set by each experiment. As any complex system, CERN computing environment may behave unstable due to various levels, due to various reasons. Some issues can be on the application level, on middleware level, network level, resource level, and issues can be caused by different reasons. So, you should understand that many workload and data management routine operations are already automated at CERN, of course. And here I outlined the routines which has already been automated. For example, job dispatching and scheduling, brokerage of physics analysis tasks, recovery of failed jobs, for example, replication of popular data, deletion or archival of unused data. Sometimes when some resource are failed, it can be automatically excluded from the global infrastructures. However, most issues still need to be spotted manually by teams or operators, and some of them need the intervention of experts to be resolved. Operators of various teams are constantly checking several sources of aggregated information, such as test results, system performance metrics, or system logs, to analyze possible issues and take appropriate actions. Often, some failures in one subsystem or facility can generate failures in a multitude of other systems, causing some kind of avalanche effect. Operators need to be able to correlate various sources of information to find the root cause of the issue. Once this cause has found, it may either be solved by the operators themselves following documented procedure, or escalated to the relevant experts. And this escalation is currently being done either in the form of email, chat, meeting, or most frequently by using a ticket system like Jira, Snow, GGUs, etc. It's a ticket system which helps to notify about some issues. So currently, experiments at CERN claim to have about 100 persons involved at various levels in global computing operations. It means that 100 persons are involved in the monitoring of system and fixing some failures. And of course, all these people find some issues and create tickets, notifications about failures. And the number of tickets is quite big. And it requires a lot of time sometimes to resolve the issues. For example, sometimes when some operator find the issue and create a ticket in ticketing system, and to the resolve of this issue, it can have several days. So it's quite a lot. And this slide, this picture, you can see, it demonstrates the monitoring and maintenance operations today, how it is today at CERN. And so human power is highlighted with orange, and computing power is highlighted with green color. So you can see at the top of this picture a number of people. They are operators or analytics which are monitor distributed computing environment. Yes, by the way, I see the chat. If you have questions, you can ask here, and maybe I try to answer them now or later. Please feel free to ask. So these experts, these operators, analyze all alerts or signals from various devices. And they have to explore, to observe some specific plots, tables, and monitoring systems. And looking at this different visualization, etc., they try to localize the issue and the failed components maybe of the infrastructure. And after that, they create issue tickets, notifications. It's like a notification with the description of the issue. And this tickets is sent via email, chat, Jira, and other issue systems. And then responsible executors perform some actions and to correct the situation, to fix the problem. And to maintain CERN computing infrastructure, we need a lot of operators, which write a lot of issue tickets daily. So what we want to do next? What will happen tomorrow? As all the issue tickets is saved in the database and all the descriptions and all proposed actions of system administrators, so the next stage is to analyze all information about these alerts, about problems, about issues, and about methods for solving them. We can use all accumulated data from all issues to train machine learning algorithms how to respond to a particular alert. As a result, it will allow to automate some user actions, some actions of the operators. And then operations after tomorrow. And ideally, we will significantly reduce the amount of human resources, of required human resources, by shifting most of the routine work of processing alerts to a computer. And that's the main goal of the operational intelligence project. We want to automate as much as possible. But it's not limited to it. This project have a lot of analytics initiatives in various fields. One of the most important is the analysis of log messages. Because you know that analysis of failure logs, of error messages, is one of the central component of all analytics system of monitoring systems. issue understanding and mitigating can be improved by preprocessing, combining, and correlating data from different sources. And here you can see examples of textual error messages, which often allow to detect the reason of the issue. And now operators at CERN analyze all these error messages, in fact, manually, by hand. But the complexity of computing system is constantly rising, and it provokes growing of the number of these error messages. And more human resources are needed to read and explore all these messages. But this process can be automated, and our team is involved in this process. And on the next slides, I'm going to show how we do it. But first, if we talk about the number of failures, here is a great representative example. It's a plot with a distribution of job statuses for each hour during one day. For example, and here we can see that jobs which failed with failed jobs is about 10% of all completed jobs. When I say job, I mean that it's some physics analysis or data processing job carried out in the distributed environment at CERN. So, for example, on this plot, we can see that we had 1.5 million jobs, completed jobs, for one day. And it has about 160,000 error messages. Sometimes the number of failed jobs may be much bigger, up to 2 million, for example. And each error message is stored in a database. And of course, we need to have some specific tools allowing to analyze the error messages automatically, not to do it by hand, as the number of errors is quite big. And on this slide, I presented some methods, some existing methods for parsing and analyzing logs. So the picture on the right shows what the log is and what's the result of the log analysis. So a log is a string that contains a date, timestamp, a mode of the log. It can be warning, debug, info, and error, and the error message itself. And the parsed log is a presentation of data in a structured form. Thus, in messages, the main part is separated from domain-specific part, for example, from IP addresses, line numbers, file path, URI, etc. In total, there are about 13 applications. They are listed in the table at the left. These applications for tools to analyze, to parse logs, and they can be classified by different methods. Some of them use frequency pattern extraction, some of them use machine learning, and some of them use heuristic methods. And also some of them are fast, some of them slower, and only 5 of them are open source. I won't stop in detail on these methods because it's not applicable to the analysis of error messages for CERN computing. We can't use these methods directly since they are essentially aimed at looking for similar text patterns, only similar text patterns in error messages. But our task is to perform such an analysis that will allow us to group error messages not only by text patterns, but by semantic content, by the initial reason of error. What I mean, for example, all messages, we need to group all messages that indicate, for example, that server doesn't have enough memory in one group. Messages that has some authentication error in another group. If you can, as you can see on this slide, for example, no such file or directory messages in next group. Copy failed, another group. But in spite all these messages in these groups has the similar problem, the similar issue, you can see that text patterns may be completely different. And our goal is to categorize messages automatically by the reasons. On this slide, there is a general stages of our clusterization algorithm. The stages are tokenization, vectorization of tokens, vectorization of messages, and clusterization. A few words about each stage, because I think it's very important, and you can maybe use some of these methods in your research, for example. Tokenization is the process of dividing the text into sequence of smaller parts, words, tokens, symbols, digits, etc. And it's these parts are called tokens. So the list of tokens and then used as the input for the next text processing stage, vectorization. When we tokenized each message, each error message, we can build a vocabulary which include all tokens from all error messages. So the next stage is to represent each token by a set of numerical parameters. So for your understanding, when we have initially the text, we need to clusterize some strings. The first thing we should do is to convert these strings to numbers, because we can clusterize strings, but we can clusterize numbers. So the main question is how to convert these strings to the numbers. After tokenization, we vectorize each token. We built a vector space model of tokens using word-to-vec algorithm implemented by Google in 2013, and I'll explain this method at the next slide. After we vectorize tokens, we have to vectorize sentences, messages. And this the third stage. Messages vectorization is a mathematical average of the vector representation of all tokens in the initial message. And then a vector model of messages is used by clusterization algorithm to split all messages into similar groups. So that's a simple description of the clusterization pipeline, but of course it has much more interim stages. I just won't tell about them as they are very specific and we don't have enough time to cover it all. I'll tell only about some important stages which I hope you can then explore more detailed and use in your investigations. So at the next slide, I wanted to show how we build the vector space model of tokens. For this, we use word embeddings method. The main idea of this method is that the meaning of each word can be inferred by its neighbors, by its context. Word embedding is a set of techniques in natural language processing where tokens from vocabulary are mapped into numerical vector. This mapping is implemented using neural networks algorithms. And the result, each term, is represented within the context in which words, in which tokens it appears. At pictures below, there are examples of numerical vector representations of token. For example, you can see the vector which has multiple features, and these are representation of one token. But you should understand that all these features in this vector, they in general, they don't have any meaning, like, for example, position of token or frequency of token. These features just represents the model of a context for this token. And if we try to highlight it, each feature value by some color, from red to green, we will see that this vector are coded as a context of tokens. And using this representation, we can search similar tokens, and the similarity is defined by similar context vectors. As an example, I provided most similar tokens for words source and word destination, and these two words are mentioned together in a lot of error messages. And we can see that really word-to-vec model thinks the same. The most similar word for the source is destination, and vice versa. So a word-to-vec model is very useful, and it allows to decode each token by numbers describing their context. And it means that the word-to-vec model represents the meaning of tokens. And we used it in our clusterization method. And another point which I wanted to highlight here is the clusterization method algorithm. You know that there are a lot of different algorithms for clusterization which allow to split data into groups sharing similar parameters. But most algorithms require to install some initial knowledge about data. For example, they require the knowledge of the number of clusters. How many groups or clusters do you think your data may have? But in our case, when we analyze error messages, which may be absolutely different, which may have absolutely different various textual pattern, we don't know in advance the number of clusters, the number of groups. It can't be predicted anyway. So the DBSCAN is one of the algorithms which don't need the number of cluster, and we can use it. The density-based clustering algorithm makes an assumption that clusters are dense regions in space separated by regions of lower density. Since these algorithms expand clusters based on dense connectivity, they can find clusters of any shape and doesn't require to specify the exact amount of cluster. Instead, it requires two parameters, this algorithm, the epsilon and the mean samples. The epsilon parameter is the maximum distance between 2 points to be considered as neighbors, to be considered as belonging to one cluster. So it can be said that epsilon is intra-cluster distance between points. And mean samples is the number of samples in a neighborhood for a point to be considered as a core point. And so the epsilon parameter is the most important for clusterization, and it can be calculated based on data. And we do it based on data, and we have some additionally stages in the clusterization pipeline to detect this epsilon parameter for the DBSCAN. And as a result, finally, we apply the DBSCAN algorithm to represent numerical representation of error messages, and it groups all messages into clusters, and the results are quite accurate. For example, like this. On this slide, I showed some results of clusterization of messages. Here is the fragment of table describing detected groups of error messages. The first column is the size of a group. It means how many error messages are in this group. The second column is the textual pattern of messages in this group. And the third column is the automatically extracted keywords and key phrases of all messages in the group. So now this clusterization pipeline is under development, and we are going to integrate it in CERN computing environment very soon. And our next goal is to learn how to group messages automatically by keywords, key phrases. Like here, for example, to group messages with authentication errors, or to group messages with login errors separately. And it should be done automatically without human intervention. I think that I can finish at this. And this slide is about our other research. For example, what we can do else about the monitoring and data analysis for CERN. Another directions of our investigation is the parallel coordinates visualization for the analysis of high-dimensional data. It's also done by MIFI team, and we have already good results with it. Also, we are involved in the analysis of slow computing tasks. It means that in CERN computing environment, some user analysis tasks can last more than 2 weeks. And we try to analyze why it happens and what we can do to avoid such time delays. And finally, now we started a research of data popularity for user analysis. Data popularity, it means that all data sets at CERN may be popular and may be less popular, and the popularity measures are used for data placement, for data distribution, to make replicas of data, or to delete this data. This popularity measures are very important, has become very important, especially when after the LHC upgrade, when the amount of data, the volume of data will grow up significantly. So this is the overview of our investigations. So I'll try to turn on my camera. Finally, I provided some resources. First resource for a Russian speaker. It's the paper of our colleague from CERN. Another paper about the networks. And finally, 3 and 4, it's about the log clusters. So below there is my CERN email. So if you have some questions, you can write, and I'll try to answer. So I think that we can finish. I think that the information was that we have a lot of information, and it's of course not easy to understand it from scratch. So if you have any questions, you can ask here, please.
Yes, thank you very much, Maria, for a very interesting webinar. So, are there any questions for our speaker today? Please, you're welcome, or in chat, or I can go on the air. Well, I have one question, I think. Can you guide us on the BERT technique?
Unfortunately, I don't know what's the BERT technique.
Maybe I...
maybe it's some abbreviation. We just
Well, I can connect the participant to our conference to say the question, okay? Okay.
So I see next question about choosing clustering algorithm. It very depends on the initial data. For example, when we worked on the algorithm for log analysis, we tried different clusterization algorithms like DBSCAN, optics, DBSCAN, which don't require the initial number of clusters. And how to say, we decided that DBSCAN provides the best results, the most accurate results. There is no answer to this question. You need just to try different algorithms and look the results. It very depends on the data. About which laboratory I work at CERN, I don't work at CERN laboratory. I just collaborate with CERN, and especially but I work at Moscow State University. So, more questions? I still wonder what's this BERT technology, because it's something very familiar, but
well, the participant is not in connection with us. Some problem with the internet connection. Well, any question for our speaker, please?
I see one question about job parameters. Wait a minute. I think it's corresponding to this slide. Closed jobs. No, closed jobs doesn't mean that they failed. It just means that these jobs were closed by some reason, and it will be re-executed. So
We have a question about the bed technology.
Mm-hmm. Mm-hmm. You know, I didn't use this. Maybe I should investigate it separately, but currently we use only word embeddings, and it provides quite good results. So about BERT, unfortunately, I can't answer. Have no experience in this yet.
Well, I think if we have any question, our participants can send it to your email address and connect with you by the email.
So again, the last slide, yes, with my mail.
Well, thanks again, Maria, for participating for this interesting lecture. To our audience, thank you, and we will. I think we will meet one more. It's interesting for our audience. That's why.
Andrea,
thanks a lot. And yes.
Yes, Andrea, I see a question. How does MEFI connect it with CERN? I think it's very important. Maybe you can answer.
Yeah, of course, yes. Okay. Some of our specialists are the participant of CERN collaboration, and in different spheres, or in a question of high matter, or high matter, dark matter, or in the question of visualization and IT infrastructure. That's why it's very very wild field to connect with the CERN and different experiments in this physical sphere.
Yes, I can add that I know that MEFI has a very wide collaboration with CERN in terms of physics, in terms of high energy physics. And CERN has a lot of physics from MEFI working at CERN. And now we started the collaboration in terms of computing. So
in some ways of detectors, in some way of computer science, it was some interesting sphere of experiments with the. Well, I try to remember. Okay, if I send to our participants the information, if it's interesting to them, about our connection with CERN, because we have about 25 to 30 participants of this collaboration by MEFI. Yeah, Maria?
Yes. I agree. Okay, I think there are no more questions. And if guys have, please feel free to write me.
Yeah. If no more question, we thanks again our speaker today, Maria. Thank you.
Thank you.
And I hope that it not enough our webinar with you. See you later. Thank you.
I hope to. Okay. See you. Bye.
Bye.
Bye.